All right, so we'll look more at the specifics of fusion reactions like hydrogen fusion and exactly how we calculate that for the sun a little later on. But what I wanted to do next was to look at this portion of the binding energy per nucleon graph, in which the elements are bigger than iron and naturally tend to give off energy as they break apart into smaller pieces. And so that is associated then with different methods for radioactive decay. Remember that these tend to work best for elements that are bigger than iron, but not always. You do have some radioactive decay for elements that are smaller than iron too, because the proton and neutron numbers have to maintain a certain relationship to each other. And so that can cause an internal jostling of the nucleus between the neutron and the proton numbers, even for smaller elements, like for example carbon-14. Carbon-14 is radioactive, and you'll see that if you do, carbon-14 is one of the elements that you make in lab using that computer simulation. You'll see that it's unstable and it tends to have a neutron turn into a proton, gives off a beta particle, and that causes it to decay into nitrogen. Okay? And so even though I'm going to be dealing with bigger elements here and those types of radioactive decays, we don't want to think that just because we have an element that's less than iron on the periodic table that we can't get radioactive decay. We still can. But the main process that drives radioactive decay for elements greater than iron is going to be due to these atoms wanting to maintain and gain their most stable configuration, which is the iron nucleus. Okay. So that being said, let's look at three different types of radiation processes that can take place. We have alpha radiation, beta, and gamma. When we talk about alpha radiation, we are talking about the release of a helium nucleus. Okay, so typically then we won't have orbiting electrons around this thing until it actually is ejected from the nucleus. But this is just a stable configuration for matter to leave the nucleus because helium has the configuration of a completed, what we call shell structure. Okay? But you go, wait a minute, you're talking about atomic, not nuclear. Well, it turns out nuclear too. You've got energy states in the nucleus that satisfy the Schrödinger equation that are in some sense analogous to the atomic energy states. So it turns out that an alpha particle's nuclear states are also very stable, just like its chemical states are if you had orbiting electrons going around it. Okay, so here we have some element A prime going to a smaller element. Now here, because it's an alpha particle, that has a proton number of Z minus 2. Well, the alpha particle's 2, so the resulting nucleus will have a number Z minus 2. The neutron number will be N minus 2. And the nucleon number will be A minus 4. It'll be plus our alpha particle. And then if this is a reaction that is favored for nuclear decay, there'll be a positive value for Q. Now, does every single atom that's bigger than iron want to decay like this? No. Most of them, as a matter of fact, will have Q values that are negative. And if that's the case, then that reaction just doesn't go. Okay? But the ones that do have a positive one mean that there's a shift in the balance of the proton and neutron ratios that is favorable for the reaction to take place. Remember that typically the neutron to proton ratio for large elements is about 1.5. So if we, so these nuclear decay processes try to maintain that ratio of the neutron number to the proton number. And that's what helps to define whether this reaction will go and give off a positive amount of energy. Okay? Now, other forms of radiation that we'll talk about in more detail after I do an example here are beta. And now beta is the release of a nuclear electron. So we actually get a transmutation of a neutron into a proton in the nucleus. So beta decay processes actually increase the Z number, make the element go to a higher proton number, higher element, but with the same mass. The same mass number, because an electron doesn't affect the atomic mass number. So in this process then a neutron becomes a proton, and a nuclear electron is ejected from the nucleus. This has nothing to do with the orbital electrons. So the orbital electrons are part of the atomic energy states, and here we're talking about nuclear energy states. Here, remember, the nucleus is very small. And so the energies are very, very high because the protons are so close to each other that there has to be a huge amount of binding energy to overcome the repulsive forces of the protons. And so that's why you get MeV of radiation in a nuclear process and just EV of radiation in an atomic process. Okay. And then finally there's gamma radiation. These are just high energy photons that are caused by a nuclear de-excitation. So the nucleus can decay to a lower energy state. So you can get an excited nucleus just like you can get an excited orbital electron state, which is what's called an excited atomic state. But here in the excited nuclear state, you can give off gamma ray photons. Okay, so let's look at some specific examples of how we could work this thing through. And with my first example, I'd like to take a look at the radioactive decay of thorium into, here we know, thorium is element number 90 on the periodic table, and we want to turn that into radium. Okay, so here we have the reaction that I want to show you. Here we have element number 228, thorium. There are some nuclear reactors that use thorium instead of using uranium. And so thorium is element number 90 on the periodic table, and it will tend to, over a certain length of time, decay down into radium. Okay, so this is atomic number of 88, and the atomic mass number here is 224 plus an alpha particle, which is 2, 2, 4. And then that will give off energy. Okay, so this is a process then of gaining energy from the radioactive decay of thorium into radium. So how does this actually happen? Well, we have a nuclear potential, which perhaps looks something like this. So here's our U value, and drops off like this. And so here, inside of the nucleus, we have an alpha particle. That alpha particle has an energy that's less than the maximum energy of the strong nuclear force. So what the alpha particle is going to tend to want to do is to tunnel through this barrier so that it can escape. So this is the alpha particle after quantum mechanical tunneling. So is this very probable? Well, not that probable, because it doesn't happen all the time. The half-life for this kind of a reaction could be a considerably large number of millions of years, okay, for this thing to happen. But it does happen occasionally if you have a lot of these things in one place. Then you statistically get a few of these decaying all the time. Okay? And so this wouldn't happen if it weren't for tunneling. Okay? But here we've got the alpha particle trapped in this nuclear energy state that is associated with the thorium nucleus, and then you get it escaping, and then the radium is left over. So to figure out the Q value for this, you can say that Q then is going to be equal to the mass of the thorium times c squared minus the mass of the radium times c squared minus the mass of the alpha particle times c squared. And so this one should weigh more than these two. That's the opposite of fusion. In fusion, the fused nucleus weighs more than the masses of the individual, or weighs less, I should say, whereas here it weighs more. Okay, so now if we look up the mass of thorium, here we've got, this is 228.08776, sorry, 227. Mu minus the mass of the radium, that's 224. These, of course, would be numbers that I'd have to give you for an exam. 0.080429. Mu minus the mass of the alpha particle, which is 4.002603. Mu. And then this is all multiplied by c squared. Remember that we're using the equivalent form for c squared is 931.5 MeV over mu. Okay, and so this will all just crunch out to become a number in MeV. So when we plug all those values in, we end up getting 5.304 MeV. So that's how much energy is given off in this reaction. But as it turns out, the majority of the energy is going to go into the smaller particle. Okay? And so this is just a consequence of combining together the principles of conservation of energy and momentum at the same time. And when we do that, what we end up with is the kinetic energy of the alpha particle is equal to A minus 4 over A times Q. And so what this is showing us then is that for large values of A, where A is the original atomic mass number of the thorium, almost all of the energy goes into the alpha particle. In this case, this would be 224 over 228 times the Q value, 5.304. And that gives us 5.211 MeV. So the vast majority of the kinetic of the energy of this reaction goes in to this very rapidly moving alpha particle. And very little of it goes into the recoil kinetic energy of the radium. Okay, so here we're looking at just maybe a % or 2 of the total energy goes into the radium, and something like maybe 99% or more of the energy goes in to the alpha particle. So this is the kinetic energy of the alpha particle. So this is the reason then why radioactivity is so dangerous, is that you've got these little bullets, and these bullets just go flying through you at high velocity. And so that can do a lot of damage to your tissues. And so if I just threw this pin to somebody, I wouldn't be worried about it. But if I put it in a crossbow and fire it really fast, then you jump out of the way. You know it's going to cause some damage. And so it's not that the alpha particles themselves are dangerous if they're not moving fast. It's that they are moving fast when they are associated with a nuclear decay process like this alpha decay process. And so that means that they can do damage to your bodies. Now, if we look at this reaction and then we compare the Z, N to Z values for these two, what we find is that the N to Z ratio for thorium is going to be, well here, this is 90 plus what is 228? Well, that would be, what, 138? Is that what this would be, 138? Yeah. So that'd be 138 divided by 90. Which is 1.46. Now let's see what the N to Z ratio is for radium. This form of radium is going to be, well, 224 minus 88 is 136 divided by Z, 88. And that's 1.54. So this reaction tends to go because the N to Z ratio was a little lower than 1.5, but then it overshot a little bit in the other direction. And so this 1.54 tends to indicate that this one might still not be quite stable and might tend to decay again. So what would radium tend to decay into? Well, radium, if it has another alpha decay, will decay into element number 86, which is radon. And so we're part of a natural decay radioactive sequence in which in this case, the alpha decay, is adjusting the neutron to proton ratio to optimize that ratio. But it's not quite happy until it reaches a point of greater relative stability. And so we'll notice here then that what seems to be happening during this alpha decay process is that the N to Z ratio goes up. Now, why is that true? Well, if we look at this reaction here, what we see is that if you take 2 away from the proton and 2 away from the neutron, both, then as you get to smaller numbers, let's say the number here was, you had 2 more neutrons than protons, let's say. Okay. And so let's say you had 0 protons and 2 neutrons, or I'm sorry, let's say you had 2 neutrons and 2 protons and 4 neutrons. Okay. And so you produce an alpha particle from that, then this is going to go from 2 to 0, this is going to go from 4 to 2, and so your N to Z ratio then essentially goes to infinity, because then you'd have 2 over 0. And so you can see then that even when the N and the Z values are similar to each other, if N is greater than Z and you take the same number away from both, 2 in this case, that's going to cause the ratio to go up. Not going to go to infinity, but it's going to go up a little bit, because this isn't close to being 0, right? This is 136 and 88. But still, this will cause the N to Z ratio to increase. So typically the reactions will be favored if you end up with a nucleus where the N to Z ratio is a little less than 1.5. Whereas in a beta decay process, it's the opposite. In a beta decay, this is the other side of the coin. If the N to Z ratio starts out greater than 1.5, then beta decay is going to be favored. To bring it back to 1.5. Okay, why is this true? Well, because a neutron is being turned into a proton. Okay, and so that's going to lower the N to Z ratio. Because you're taking a neutron and turning it into a proton. So you can see that that lowers the N to Z ratio. It's easier to see than with the alpha process. And so our basic reaction then for beta decay is going to look like this. We're going to have our X prime nucleus with a Z, an N, and an A value. And then that's going to go to our X nucleus. But because a neutron's being turned into a proton, this will be Z plus 1, this will be N minus 1 and A. And this will be plus a beta particle. Now, a beta particle has a Z number of -1 and 0 mass, atomic mass number, and 0 neutron number. Okay? And so this is a nuclear electron then that is associated with the beta decay process. And so this makes bigger elements then. So if you want to make larger elements, you do beta decay. For example, you could start out with a U-238. Sorry, this is 92. This is 146 and 238. And then if you add, if you allow this to transform into something else, in other words, you allow it to decay, this ends up being Neptunian. And a Neptunian has an atomic Z number of 93. It has a neutron number of 145 and still an atomic mass of 230. Here, let's start with, sorry. Let me just start this by adding a neutron to U-238. And so I can do this then if I have a source of neutrons. And so then this will turn into U-239. But now the U-239 has a Z to N to Z ratio that is way greater than 1.5. So if we look at this as N to Z, 147 divided by 92, that gives us, oh, that's horrible, 1.59. That's getting way too big. Okay, and so although this nucleus can form, it tends to be unstable because its N to Z ratio is too high. Okay, and so, oh my gosh, we've got to hurry up and do something about this. Beta decay, remember, is the way to lower the N to Z ratio. We can see here that it's way too high. So this is often done in a nuclear reactor. You bombard U-238 with uranium, and then that creates an isotope of uranium, which is even more unstable than the regular uranium. And so in a matter of just a minute or two, this will tend to decay down into Neptunian. Now we say decay down, it's actually going to a higher value for the Z number. It'll still have the same atomic mass number of 239 because electrons don't affect that. But it's going to take one of these neutrons and turn it into a proton. So this will be only 146 neutrons. And that'll be plus our beta particle, which is going to be minus 1, 0, and 0. Okay, so we've made a little bit of Neptunian. But if this is for the N to Z ratio for U-239, let's check it out for Neptunian 239. Is that going to be happy with that ratio? Well, maybe not. 146 divided by 93. It's going to be less than 1.59, but I'm still guessing it's going to be greater than 1.5. I hope it is, because I'm saying that it will be for this example. Yeah, still 1.57. Okay, so that's still too high. So after another couple of minutes, what it's going to do is it's going to want to beta decay again. Okay, so the Neptunian then, 93, 146, 239, will then, quote, decay into plutonium. Now, plutonium is one of the most toxic substances that has ever been constructed on the planet Earth. It's element number 94 on the periodic table. It'll still have an atomic mass number of 239, but now it'll have 145. And so this is more stable and has a half-life of about 25,000 years. And so we've been able to make the plutonium then by having it emit a beta particle. This is -1, 0, 0. Okay? And so these processes, once the uranium becomes excited, go to Neptunium and then to plutonium. And then it turns out that plutonium is easy to bust apart. Okay? And so it's perfect then for either a something that will help to accelerate a nuclear reaction in a nuclear power plant, or more importantly, it could also be used as a bomb. And so that's what we have to be very careful about when we allow countries to have nuclear technology, is that they can just sit there and let the U-238 be bombarded with neutrons, then do a couple of beta decays, then they could do some centrifuge operations, distill out the plutonium. If they can get that to, say, 70% pure, then you've got an atomic bomb. And so this is something that, because it has a half-life of 25,000 years, none of this is around from when the Earth first formed, because the Earth has gone through so many 25,000-year time periods since the beginning of the solar system that we have to make these things. And so that's how we make some of these heavier elements, is we use a nuclear probe to bombard the biggest naturally occurring element, U-238, turn it into an unstable isotope, U-239, then let it do a couple of beta decays, which eventually brings its neutron to proton ratio down to a more manageable level. So here the neutron to proton ratio for plutonium is 145 over 94. So that's more reasonable. It's something that it can live with without having to decay quickly into something else. It has an N to Z ratio of 1.54. And so this seems to be in a more stable range. So that this can sit around for 25,000 years before an average atom will decay down by means of, say, alpha decay into a smaller element, or in a nuclear reactor, of course, you can accelerate this reaction considerably. Okay. So that's the basic idea then with what you can do with beta decay to make a heavier or bigger element out of a lighter element. But let's actually do a calculation. And for this one, I'm going to take a different example, different kind of example. For beta decay here, let's do beryllium to boron. So we have a beryllium atom. And here, let's say this is beryllium 11. So that is an unstable isotope of beryllium that has an atomic number of 9. So beryllium then is element number 4. Now normally the number of neutrons would be 5, but in this case we'll give it 7. Okay, so that's an unstable isotope of beryllium. And so that's going to want to, because the neutron to proton ratio here, N over Z, is 7 over 4. So that's equal to 1.75. So that would be high even if we were in the large Z approximation. But here in the small Z approximation, we want N over Z to be 1. So this is really going to have a tendency then to want a beta decay because the N to Z value is way, way too high. So what it could do then is it could change into boron, which is element number 5 on the periodic table. The neutron number would be 6, and the atomic weight would be 11. Now we can see here that that is pretty close to the normal average value for boron. Boron, although N equals Z for the most part, it's not always equal to Z. It turns out that this is the most stable state for boron, is to have one more neutron than it has a proton in the nucleus. And so this will be plus a beta particle that is emitted. So then we can calculate the Q value for this reaction, and so that's going to be equal to the this has a natural tendency to want to go this way, okay? And so this one is going to be the bigger value, mass of the 11 BE47 MC squared minus the mass of the 11.5 boron 6. We could almost guess that this one is going to have a bigger mass because it has more neutrons relative to protons, and we know that the mass of a neutron is greater than the mass of a proton. Okay? So as we go to lower neutron and neutron to proton ratio similar, we know that this mass should be a little bit less than this one because this has disproportionately larger number of neutrons to protons. That would be minus these two masses times the speed of light squared. What about the mass of the electron? Well, turns out the mass of the electron cancels when you write this in terms of atomic mass numbers. You can show that the electron mass doesn't enter into the Q calculation. And that's something that I may show later, but I'm just going to state that for now. So you don't have to worry about the mass of the electron in this Q reaction. And again, I can prove that that's true, but I'm not going to do that right now. Okay, so if we plug in the tabulated values for the nuclear mass of beryllium and for the nuclear mass of boron, what we end up getting is 11.021660 mu minus 11.009305 mu times the speed of light squared, which again is 931.5 MeV over mu. So that gives us a Q value for this reaction of 11.509 MeV. And here, almost all of this goes into the beta particle. So we can call this Ke beta. It's approximately equal to Q. Because here, the difference in mass between the beta particle nucleus and the other nucleus is essentially 1. So it's almost 100% of the energy goes into the beta, whereas something like 98, 99% of the energy went into the alpha particle during an alpha decay process. Almost 100% goes into the beta particle. So the beta particle, again, could just go right through you, and it can cause significant amounts of damage to the human body. Okay, now a little later on, I'm going to talk about examples of gamma ray. But one last thing I wanted to look at in this lecture is the mathematical technique for determining the radioactive decay rate. So let's do this for a plutonium atom. Let's say that the half-life for plutonium is equal to 25,000 years. Now, I haven't really defined clearly what I mean by the half-life, so let me do that here. This is the amount of time that it takes statistically and randomly for a given atom to decay in such a way that half the sample will have decayed after the half-life time period. Okay, and so let's find, first of all, an expression for the decay rate. Okay, now, decay rate we could do in units of, say, decays per second. And we find that that decay rate is equal to minus lambda times dn dt, where n is the number of radioactive particles you have. So dn dt, our decay rate, is equal to, we call here a decay constant, multiplied by the derivative of the number of radioactive decays that you have per unit time. Okay? And so let's find the expression for n as a function of t. So let's say we have a certain number of radioactive particles, n, and at some initial point we have n naught. And n naught is the initial value for the number of radioactive particles. Then we can write n of t is equal to n naught e to the minus lambda t power. Sorry, here this should be number of particles in terms of decay rate. Could we stop that for 1 second, Mark?